So in this lecture, we continue with the matrix algebra, and so far we talked about equality of matrices. We talked about addition of matrices and multiplication of matrix with a number. So what's missing is naturally, what's missing is multiplication of matrices. Later on, we'll talk about the division of matrices. You will see that it's already complicated, the multiplication. The division is even more complicated, okay? So in order for us to before I start, talking about the multiplication of matrices, the formal definition, which is very complicated, is the same goes with vectors, for example. Just to give you an idea, remark here. If you look at vectors in geometry, in R3, okay, in space, and you look at U times V, okay, we have all the properties the same, but when you look at U times V, which is a vector, okay, so sometimes it's called the product, the vector product, and sometimes it's called the cross product. And in fact it's very, very complicated and not natural, absolutely not natural. Okay, for example, we know that U cross V or U times V is equal to V minus V cross U. There is a minus, which, by the way, it's not normal compared to the product of two numbers. Okay, so in fact, when we go to higher dimension other than the product of numbers, the product or the multiplication becomes complicated, okay? And it's not natural at all. So in the case of matrices, it's the same problem, okay? It's the same problem. So it was done by a French mathematician. His name is Binet, around 1800 and something. And the way he looked at it, he looked at a matrix is just a form or a representation of linear transformation. And the product comes naturally from the composition of two linear transformations. So the product of matrices was born as the representation of the composition of two transformations. Okay? So I will explain a little bit. This is a little bit fuzzy, and this is a little bit not clear, but we'll make it clear. You will see it a little bit more and more. So we'll attack this problem from the systems. We're gonna go back to the systems, get help from the systems, and from there we will say something, and you will see that what Binet was trying to do and what Binet is talking about. Okay, so do not worry about it. Okay. So, as I said, let us start with an example. So let us take a linear system with two equations and three unknowns. So the unknowns, we'll call them x, y, z. So it's gonna be, it's just an example, huh? 2x minus y plus z equals to 1, and 3x plus y minus 5z equals to 2. Okay? And this can be seen as, we can see it as a matrix representation here. We can go to matrices and play with matrices. We did that at the end of the previous lecture on introduction to matrices. So this becomes 2x minus y plus z equal 1, and 3x plus y minus 5z equals to 2. Okay? And keep in mind, so we have the coefficient matrix, not the augmented matrix, the coefficient matrix, which is 2 minus 1 and 1, 3, 1, and minus 5. Okay? And the unknowns, let's put them into unknowns, x, y, z. Let's put them as x, y, and z. Okay? So the way to look at it is, we have the matrix 2, 3, minus 1, 1, 1, minus 5. Okay? And let us assume for a second we multiply it by x, y, z to get the end result, which is 1, 2. Okay? So this form can be seen as a matrix representation of the system, in other words. Okay? So we have the coefficient matrix, we have the unknown, okay, and then we have the number 1, 2. So the transformation that Binet was talking about, he looked at the following: x, y, z, okay, and he associated to it the 2, 3, minus 1, 1, 1, minus 5 times x, y, z. That's how he looked at it. This is the linear transformation I was referring to. Okay, so in any case, what did we do? Okay, so again, let's look at the products. How can we see the products? So we have, so let me go back here. So basically what we have is 2, 3, minus 1, 1, 1, minus 5 times x, y, z equal the system that we had. Okay, so what do we have? 2x minus y minus 5z, and then 3x plus y minus 5z. Okay, this is not minus 5z, sorry, plus. Okay, so how do I see this? This is how it goes. First of all, we are gonna take the first row and multiply it with the column x, y, z. How? Okay, so we will define this way. So we have, let me put in a different color. So we have a, b, c time x, y, z to be ax plus by plus cz. Okay, so we are dealing with, so we have this one times this one times this one, and this one times this one, and we add them. Okay, so this should remind you something about the dot products of vectors in R3 or the scalar products. So we have the dot product, sometimes known also as the scalar product. So we have, this is just a definition, huh? So x1, x2, xn times y1, y2, yn, and this would be x1, y1, x2, y2, and xn, yn. Okay? So keep in mind that the sizes now, let's go back to matrices and let's use the sizes because we have a row vector versus times a column vector. So what's the sizes in terms of sizes? So we have 1n time n1, and the end result is a number which is 1 by 1. Okay? So if you go back here, okay, so what do we have? We have 2 rows, 3 columns, 2 by 3, 2 rows, 3 columns, and we have here 1 column, 3 rows, so 3 by 1, 3 by 1, and when we multiply them, what did we get? We got 1 column and 2 rows, so 2 by 1. So what happened? Basically, what happened is that these two numbers are gone. The end result is the first number, which is the rows, and the last one, which is the column, so 2 by 1. And here, when you look at here, because in order for us to do this, the number of columns should be exactly the same as the number of what? Of rows. Otherwise, the dot product doesn't make sense. The dot product doesn't make sense. So we are talking about this number here should be the same as this number. So this suggests the following, which is that if you want to do a multiplication between two matrices, so the following here is very important. So the following remark, so here now, all this what we're discussing here suggests the following. So the work of being A, basically. So here, remark. So if A is n by m, and B is s by t, these are the sizes, then in order for us to perform A times B, okay, we must have the number of columns of A equal the number of rows of B, otherwise it doesn't work. So here we must have M equals S. And once you have done that, so what do we have now? We have N by M, that's A, times the matrix B, which should be M by T. And the end result, the M is gone, and the end result will be N by T. Okay? So in terms of how do we see it and how do we do it? We have A times B. Okay? So this is A and this is B. Keep in mind, the number of columns of A is exactly the same as the number of rows of B. Okay? Great. So now, this is how it goes. We take a column here, yeah? And we multiply it with a row. So, how many, in the row of A, how many entries do we have there? Is the number of columns, which is M. There are M entries in the row of A. And how many entries do we have in the column of B? These are the number of rows of B, which is M. So when you multiply them, you generate what? You do the dot products I told you about. And you see, so here, so you take the first number times the first number, second number times the second number, and continue this way till you generate one, and you add them, and then you add them till you generate the associated number that you want. Okay, so let's do an example here. Okay, 1 minus 1, 0, 1 times 1, 0, 2 minus 1. So we have no problem. Why? Because we have a 2 by 2 times a 2 by 2. The end result will be what? 2 by 2. Okay? So we are okay. We are safe. So now how do we do it? Okay. So how do I get, for example, this number? Okay? So this is what? This is the first column, second row. Okay? So if I multiply the first column with the second row, okay, I will generate that number. Okay? So this will give me what? 1 times minus 1, 0 times 1. Okay? Great. So here, let's do it. So we get minus 1, 0, minus 1, 1, times 1, 0, 2 minus 1 equal. So the first column now, we're going to use the first column of B. Okay? First column of B. So 1, 0 times the two rows of A. This will give me the first element of the first column, the end result, and the second one in the first column. Okay? So we get 1, 0 times minus 1, 0. 1 times minus 1, minus 1. 0 times 0, 0. Minus 1 plus 0, minus 1. Okay? And then we take the same first column of B and we multiply it by the second row of A to give me this number here. Okay? So we get 1 times minus 1, 0 times 1. 0 times 1, 0. 1 times minus 1 plus 0 minus 1. Okay. Now we use the second column of B to give me the second column of the product. So we get 2 minus 1 times this. You get minus 2 plus 0 minus 2. 2 minus 1 times the second row of A. 2 times minus 1 minus 2. Minus 1 times 1 minus 1. Add them minus 3. So this is the product between these two matrices. Okay? And we can have different type of sizes as long as we preserve the number. So, but here I want to add some. But before I go, let us do 1, 0, 2 minus 1 times minus 1, minus 1, 0, and 1. Okay, so I'm doing B times A. Okay, so what do we have? Again, we will take the first column of A times the rows of B. So we get minus 1, minus 2, minus 3. Minus 1 times 0, 0, plus 1, and then 0, 2, and then 0, 1, minus 1. Yeah? So it's amazing that, as you can see, these two matrices are not the same, the end result. For example, minus 1 and minus 3 are not the same. Therefore, A times B is different from B times A. So you see, it's not, even if you can do both products, AB and BA, is not behaving the same way as what? As the multiplication of real numbers. It's really terrible, okay? So as I said before, the moment you go to higher dimensions and you define the multiplication in some form, it's not natural. Natural in the sense that it extends naturally the real numbers. No, it's not, okay? It's complicated, okay? So, so what does it mean, in fact, that AB may not be equal to BA, even if you can do the products, by the way, even if you can do the product, okay? So this means that if you are able to perform AB and BA, we have always, if we are asked the following question, even if we are able to do it, okay, find the product of A and B. You cannot answer this question. This question cannot be answered. Why? Because it's not like the real numbers. When we say the product of 2 and 3, that's 6. Okay? Which number you start with you enter in your calculator or your computer, it doesn't matter, okay? Because 2 times 3 is the same as 3 times 2, or any numbers A, B, by the way. But here in this case, no, because we know that A times B may be different from B times A. And therefore, when somebody says find the product of A and B, you have to ask which one first, which one is to the left and which one is to the right. Okay, so are we talking about AB or BA? You have to. So you have to know which one is to the left and which one is to the right, or which one is first and which one is second. Do you understand? It's very important. Okay, so it gets complicated. My point is that it's not something, and be careful when I insisted on the fact that you may be able to do it, you may not be able to do it. If both of them are square with the same size, then you have no problem. You can perform AB and BA. But for example, if I do the following, so just to give an idea, look at a 2 by 3 matrix times a 3 by 2 matrix. What do we get? We get, again, the 3 disappears, it's a 2 by 2. Okay? But if I go now 3 by 2 times 2 by 3, in other words, AB and BA, we will get a 3 by 3. So you see, it's even different sizes, okay? And sometimes you can do one side and you cannot do the other. Like, for example, 2 by 3, 3 by 4. The answer will be what? 2 by 4. Okay? In size. But you cannot do 3 by 4 times 2 by 3. You can't. Not possible. So you see, sometimes you can, sometimes you can't. Okay? Okay, now let's go to use this product and apply it to systems. Application to linear systems. That's how we started this lecture. So what do we have? Again, let me just write it for the sake of. So we have A11x1, A12x2, plus A1n xn, n unknowns and m equations. Now, so if you remember, that's how we started. In fact, this is simply what? The coefficient matrix A1, 1, A2, 1, AM1, A1, 2, A2, 2, AM2, etc. A1n, A2n, AMN. Time x1, xn equal b1, bm. So this, okay, so let me put them both, okay? So this now is clear. What you have here, okay, is known as the matrix this is the matrix representation of the linear system. So you can write the linear system using what? The equations. Okay, that's what you have here. Or you can represent it by what? By matrices and write it in this form. And in general, the way we write it is we go A, which is what? The coefficient matrix, time, sorry, time x, which is the unknown vector, it's a column vector, x1, x2, xn, and it's equal to b, which is the non-homogeneous term of the system, okay? So here, as you can see, it's so beautiful. So this representation is exactly the same. It's so simple. AX equal B, okay? So before we close this lecture, if you go back, I talked about it in the dot product, but I don't like here the idea of one row vector times one column vector, because usually a vector is a vector. So when we talk about the dot product or scalar of vectors, okay, so the vectors, they have the same form. Either they are row vectors or column vectors, okay? So but in the dot product, the way I defined it is we have one which is row vector times one which is a column vector. So the idea here is that what can transform, because they have the same shape, how can we go from one row vector to one column vector? How? Okay, this is known as the transpose operation. Okay, so the transpose operation, for example, 2, 5, and minus 1, so it's a row vector, okay, and you send it into 2, 5, and minus 1, so it becomes a column vector, okay? So the transpose operation does this transform rows into columns, okay? So for example, if you have a matrix, and we write, by the way, here we write 2, 5, minus 1 transpose with a T, okay? So for example, when we have A, we define A transpose. So how do we do this? So the rows of A, they become the columns of A transpose, and vice versa, okay? So for example, if this one is N by M, this one will be M by N, okay? So for example, if you have 1, minus 1, and 2, 3, 2, and 0, okay, and you want to do the transpose, okay, so the columns of the matrix, they become the rows. So the first column, which is 1, minus 1, 2, okay, it becomes 1, minus 1, and 2. The other one is 3, 2, and 0. So as you can see, so we have this, which is the same as this, and we have the second column, which becomes the second row of A transpose, okay? So in the case of square matrix, so let me give you an example, okay? Example, we can see it on square matrix. So what is the transpose of A, B, C, and D? Transpose is gonna be the first column, which is AC, it becomes AC, the row. And the second column, BD, becomes BD. So basically what happened? What happened is that the diagonal, so the main diagonal stays the same. And if you look at B, it went to C and C, so this went here and this one went here. So basically what we did, we just did a reflection about the main diagonal. And this is the case for any for any, this is the case for any square matrix, square matrix, okay? So the transpose A transpose is just a reflection about the main diagonal. Okay, and before I let this go, one more definition that would be useful, okay, for some properties later on in the course on linear algebra, is the concept of trace, the trace of a square matrix. Okay, so the trace, and we write TR of A. And keep in mind, is a square matrix. It doesn't make sense to talk about the trace of a non-square matrix. So if A is equal to Aij, the trace of A is just the sum of the element on the main diagonal, meaning A11 plus A22 plus ANN. Okay, and of course, what did we say before? A remark. Okay, we said that A and A transpose, they have the same diagonal. They don't move. Okay, diagonal, and therefore they have the same trace. Trace of A equal trace of A transpose. Okay, so an example, just for the sake of, let us take an example. If A is equal to 1 minus 1, 2, 0, 1, 3, and 5, 6 minus 3. So what is the trace of A? Equal 1 plus 1 minus 3, and that's 2 minus 3, and that's minus 1.